Thank you, Dave. I really appreciate the warm welcome, and I'm always so pumped to be at YOW, of course. So good morning, everybody. I am in Phoenix, Arizona, so it's evening, but I haven't started drinking yet. Lucky for all of you. Yes, and I would like to reiterate what Michelle said. The Q&A is open right now. You can put questions in there as we go along. And also, despite everyone's recommendations, am looking at the chat right now. So I highly encourage you to pop some commentary in the chat. That's like my favorite thing about the virtual format for talks is that I can be listening to the chatter during my own talk. I know there are a few friendly faces out there, so definitely feel free to heckle. All right, shall we get started? Yes? All right, terrific. Okay, so today we're going to talk about continuous verification. Let's see, here we go. Yeah, now it's working. A little bit about me, like you're probably saying, oh, continuous verification, we haven't even started chaos engineering yet. Well, that might be, but the thing about me, I like things that are kind of on the edge of now. So things that shouldn't exist anymore, like Dave was alluding to the work that I've done with like, just ye old custom VAX operating system. I love really old things and I love things that shouldn't exist yet. So really new things. And what I mean by that, what kind of things shouldn't exist yet? Well, these are the kind of things where we don't actually know how to build them. We don't have proper regulation. Our organizations don't know how to handle them. So I'm interested in those two things that are kind of existing on the edge of now. And I think that continuous verification is kind of one of those things. Yes, which is all to say, basically, we know for a fact, right, that software changes a lot more quickly than soft tissue, our brains. So I am really fascinated by that mismatch. And I think that continuous verification speaks to that a lot. But before we get to continuous verification, what the heck is chaos engineering? If you're not familiar with it, this is kind of the definition. It's on this website, which is principlesofchaos.org, and that is straight from the folks who kind of came up with this idea. It has a little overview of chaos engineering and the principles of chaos engineering, and then some more advanced stuff. So I highly recommend you go check that out. But chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production, which is a beautiful way of asking, essentially, what if we treat failure as inevitable? So we have spent so long in software development trying to prevent failure, and it just keeps happening anyway. What is the deal with that, right? So chaos engineering instead asks, what if we just acknowledge that we are creating things that have never been created before? We're creating these complex systems that fail in ways that we've never seen before. So what if instead of trying to avoid failure, we just treat failure as inevitable and we help our systems increase the ability that they have to observe or absorb those perturbations from whatever, right? So chaos engineering basically just asks, what if we treat failure as inevitable? So that's it. Now you know what chaos engineering is. Okay, that means that now we can ask, what is continuous verification? And it, sounds kind of fancy, but I think there's actually a really easy way to explain what it is. So chaos engineering, we perform an action on the system and we ask, is this safe? We define an action and we define safety, and we perform that action on the system. And we ask, is this safe? And continuous verification just asks, what is safe? So instead of saying we're going to do this thing to this degree and see if it's safe, what we're doing in continuous verification is we are perturbing the system right to the edge of failure or to the edge of chaos. We're finding out what that edge is, and then we're backing off. So I hope that that distinction makes sense. Chaos engineering, we know what we're doing and to what degree. We ask, is this safe? Continuous verification. We are kind of, sort of telescoping in on this boundary of safety in the system, and we're looking at that boundary and how it's shifting over time. That's the continuous part. Yes? Cool. All right. I say yes, I ask yes, as if like a bunch of you are just gonna shout out from the audience at me, but you could put it in the chat. Anyway, yes. So what's going on with this edge? Why do we care about perturbing the system right up to the edge of chaos? Why are we interested in that boundary? Well, my friends, as many of you know, and especially those of you who, like me, have spent a little bit of time in operations or in a DevOps style team, you know that unfortunately, those systems are actually performing at their maximum capability right at that edge, right? So that's why they keep ending up there, because that's where they're performing at their maximum capability. So it's natural for our systems to settle into this kind of space that's just back from the safety boundary. But the, wonderful and terrible thing about our systems is that we don't know exactly where that boundary is, and it's hard to probe, right? Like, it's not a physical system where we can just see that we are approaching it. It's that feeling in your gut, right? Where you know that you're stressed out, and at this point you can't even say why. Well, that's because you're sitting just inside of that safety boundary. So you don't have to take Kat's word for it, and I honestly don't know why you would. There's been plenty of research, and there are experts and things like that. Is anyone familiar, and now I'm looking straight at the chat, is anyone familiar with this lovely bulbous triangle? Some people maybe. Okay, so this is the Rasmussen triangle, and it basically says that our operable space that we have for our business and for our systems, it has these three boundaries. Okay, so an economic boundary, a workload boundary, and then a performance boundary. And inside of those boundaries is our operable space. So I'll just explain this a teensy bit more here. So the first one is the economic boundary. And this one we all know about, right? Because this is kind of the bottom line. We have to be making money if we will survive as a business. So that's the economic boundary. We can't spend more money than we have access to or whatever. So this is the pressure towards cheaper, right? And then we have the workload boundary. And this is just that there's so much work to get done and we can't possibly do all of it. There's a limit on how much work we can do. So this pressure is towards doing things easier and more efficiently. And then we have the performance boundary, tricky little devil. This is where when we cross this boundary of performance, we are in unsafe territory for our systems. So they're no longer performing in a way that's actually fulfilling our business needs. And then what I was just describing, right, is this safety margin. So when we come just in from that boundary, we have this little bit of buffer space. And this, the way that I like to explain it, has anyone ever driven a car where the alignment is off? Yes, some people have. Okay. So when you're driving a car where the alignment is off, you can never like take your hands off the wheel for a second. You can't even loosen your grip. You have to be constantly course correcting, pulling back, because your vehicle is pulling in one direction. You got to be pulling back. So that's what this is. When we're operating in this margin, that's where you're like white knuckling on the wheel, can't pull in from that line, right? It's constantly, the system at that point is constantly trending towards chaos. And we're having to constantly introduce remediations to pull back from that line. And someone in the chat is asking, what's the significance of the line curvature? The lines are supposed to be curvy because it's not like this perfect thing, right? Those lines do have fluctuations, and we know that. And I just made up these curves because I'm not good at drawing. But you can definitely look up the real one and see the beautiful, like artisanally crafted curves that Rasmussen has there. But they're just not supposed to be straight lines, is essentially it. All right. Yes. So now we talked about the pressures. So the economic pressure is always towards cheap, right? Well, how over provisioned do you need to be? Can't you do with a little bit less? Our AWS bill is getting like really high right now. Do you really need those new machines, right? This is the constant pressure towards cheap. That's where that economic boundary is pushing us. Then we have this pressure towards easy, right, with the workload. And I'm not saying these things are bad, right? Like we need to be somewhat conservative with our money so we can stay in business. We need to find easier ways to do things. Otherwise, we'll just burn out on things that are not even moving our business forward. So the workload boundary, we're constantly just, is there an easier way to do this? Come on, there's got to be an easier way to do this. Can I decrease the frequency of performing this action? Can I automate it in this kind of way? All of these things. So there's that pressure towards easy. And then there is, so those are kind of constant pressures, right? You have those constant pressures. Well, a tricky thing in my experience about the performance boundary is that it has kind of a like not constant. It kind of like spikes up in its pressure. So basically, when we have an incident or something like that, people are like, oh my gosh, there's the performance boundary. No, that was terrible. Push back. But then it just, because those other pressures are constant, it creeps back out to that performance boundary. And we only get the pressure back in when we see evidence that we have approached that performance boundary. So even when we're inside of the safety margin but haven't exceeded the performance boundary, at that point, most of the time, most people can't articulate where that performance boundary is truly and how close you are, because you're not going to just march in there and take down production. Or maybe you are. I don't know what kind of person you are personally. But most people aren't marching into work and taking down production just to prove a point, right? So you're just having to convey to people, look, we're really close to a failure and we can't exist in this marginal state anymore. So that's the Rasmussen triangle. Now you will all have that, and tomorrow you can, or I guess 2 days from now, when is this conference over? You can march in and you have now a fancy paper to show fancy people. But it's just this. And, you know, I've already alluded to some folks and cited some folks, but a great example of some of these things intersecting is an example that Sidney Dekker gives in his book, Drift into Failure. Many of you may have seen the Safety Differently video. Last time I was in Australia, I was just shocked how many people know who Sidney Dekker is. He's obviously much more popular in Australia than he is in the United States. But his whole thing is about studying the safety of systems And in his book, Drift into Failure, he gives this great story about a famous plane crash that happened here in the United States. And what happened was there was one part, and the manufacturer said, okay, here's the maintenance schedule for this part. You're going to maintenance it however many air miles or whatever, flight miles. And so everyone's maintaining on that schedule, and they realize, okay, it never really needs the maintenance at this point. So we're going to put it in this bucket with all these other activities that happen at roughly the same schedule. It's just a little bit off. And so they maintenance it on that schedule, usually looks great. Well, then all the things from that schedule get moved into a different bucket that's a slightly more extended schedule. And this keeps happening where this part kind of gets grouped in with other things and all of this stuff. And eventually, right, you can only do that for so long and the part breaks and the plane crashes, right? But there was all of this pressure. We don't want to do an extra maintenance just for this part, push it in with the other ones, right? So we have the workload. It's expensive to do this maintenance off schedule with all the other parts. We have to keep this plane grounded, and that's expensive. Can we get the cost down on that, right? So we have these pressures, but once you cross that performance boundary, you are in unsafe territory. And unsafe means different things depending on your different industry, right? So that is Sydney Decker really based in Australia? I'm just looking at the chat. Oh, that's why everyone knows it. No one in the US knows who Sydney Decker is. All right, moving right along. So this is that quote from Drift into Failure that basically says we're always going to have this tendency to push our systems right to the edge of chaos. And what I just described for you, where we narrow that margin, that is the phenomenon that we call the normalization of deviance. So the first time that we say, well, we can push that out a little bit, or we did it this way and nothing bad happened, that's when we normalize deviance. And that's where we tend to get ourselves into trouble, and we kind of skate in closer and closer to that performance boundary. And the example that is kind of given a lot as an example of this phenomenon is the Challenger launch decision. So I don't know how many of you know about this. It did happen a while ago. And it turns out I just keep getting older, and it did happen in the United States. So what happened is there's going to be a space shuttle launch. And already some people are concerned because this part has not really been performing up to snuff. It has a fallback, but it's kind of causing people to have concern. And then the weather goes bad. It gets super cold in Florida, of all places. And then people are even more concerned. Well, we know that this part is not intended for any kind of cold weather, but we've launched so many times before with this part and nothing's happened. There's a fallback. We don't want our dates to slip. All of these things happen, and we normalize that deviance. So you say, well, we've done it before. Who cares? So I'll tell you my personal story of normalization of deviance. Okay. So this outage happens, right? We're all on the phone. We're just, everyone's pulling their hair out. And someone, this is like in a highly transactional system. So every second, so we're losing just gazillions of dollars, right? And someone says, hey, I think we need to delete this data in production. And of course, my eyes like come out of my head. I'm freaking out. That sounds like a terrible idea. But at that point, what choice do we have? So we take whatever safety measures we can, but we delete the data in production, just kind of like YOLO, let's do it. So that happens. And it's terrible, right? And we're all like, oh my gosh, that's probably like the low point of our entire careers, right? That's awful. Guess what happens again? Just a few weeks later, the same issue. We did not fix it at all. And you know what? Someone immediately hops on the phone and says, I think you just need to delete that data again. Just start deleting data in production. It's no big deal. And that became a thing, right? So we had a portion of our data that was then just dummy data, because instead of really pulling back from the safety boundary, we just became okay. We normalized that deviance, right? Like we went in the span of a couple months from saying, this is the most horrifying thing I've ever had to do in my career, to let's just put some dummy data in there so it doesn't matter when we delete it, right? It becomes normalized so quickly. Extremely not cool. And why is that? Well, you just get that safety pressure back, right? Back towards safety when there is an incident, and those other pressures are constant, right? And then what happens? Once we have some remediation, some Band-Aid that, okay, yeah, we've seen this before. Let's put the Band-Aid on it. No big deal. What happens? Then we have people saying, well, it's not an incident. We know how to deal with it. It's not an incident. Come on. Right? And people are asking you to like kind of up your threshold for what you consider an incident. And Sydney Decker and the folks who are active in those safety sciences circles, they're really interested in the near misses. And this is something that I'm super interested in, right? So I frequently with my teams have a near miss log where we just write down, I thought, S was going to hit the fan and I did this. And we look at those near misses, because that's what, even before you have continuous verification, those near misses that experts are having, right? Those tell us how close we are in some ways to that safety boundary. And so one of probably the worst things I've ever done is I became aware of this situation where it's like the nastiest in the weeds type thing, that basically control structure is broken, not doing its job, naughty, and it keeps rearing its head, and we keep having these issues. But now people are building awareness around this, and they're able to remediate it right away. Well, then I say, okay, I would please like to have money so I could fix that issue for realsies this time. People say it's not an issue. There's been no incidents now in the past 3 months around this. So at that point, I declared a 90-day incident because someone said, well, when did this start? And I decided that it started the first time that we had that near miss. And it had been persisting all along. And there goes our mean time to recovery, right? Because I just said it was happening always. It always could happen. It was always threatening. It was always looming, right? But that is the situation that you're putting people in when you normalize deviance, right? A 90-day incident sounds ridiculous, but those people who are having to deal with that, they were in a 90-day incident. They were constantly living with the stress of a major production system, tier 1 production system, could go out at any time. And it will just be a train wreck. We'll all be sitting there watching it, and there's nothing we can do, right? And so for me, I think it's only right that the rest of the organization has to at least be aware of that stress, both in the system and on the people, right? Because that's what it ends up being, where people are living in this constant state of stress right at the edge of that safety boundary. Okay, So what the heck are we going to do about this? I'm painting you a very grim picture, right? Well, now this is where continuous verification kind of enters the scene, right? So here's another quote from Rasmussen, the guy who made the triangle with no straight lines. It's becoming increasingly difficult to model systems in isolation and to make small-scale local experiments to evaluate models. In other words, sure, you should definitely have testing, right? Writing tests, very good. I highly recommend it. But you will never be able to get all the information that you need until that code is out in production, right? You will never have a perfect pre-production environment where you've created a model that can give you all the information you need to just ensure safety with 100% confidence, right? That's not a thing that we can do in the systems that we have today. So now let's give continuous verification a go, right? So again, continuous verification is where we ask, what is safe? So we are going to actually perturb our system intentionally until it reaches the boundary of safety, right? We hit that margin, and then we're going to back off, and we're going to keep asking that question over and over again so that we can see how the margin is shifting over time. How big is our operable space when we consider those different margins? And we're going to ask that in production, because with these systems, it is impossible to actually come up with a for realsies model that can give us an idea of the safety boundary, an actual idea of the safety boundary, and confidence in our system. Okay, all right. So what now, let's actually say, not philosophically, but really and truly, what is continuous verification? So continuous verification is the discipline of proactive experimentation in software implemented as tooling that verifies system behaviors. Okay, tooling. Oh, everyone's like, oh no, we hate tools, we love people. I don't know if you know this, but sometimes people need tools, and continuous verification is one of them, my friends. So yes, it very much is tooling that identifies the safety margin over time. Why do I insist so strongly that it's tooling? Because humans cannot just perfectly approach that boundary and then back off instantly before anything goes awry, right? Like a human cannot do that. Also, that would be a terrible waste of a human being's time, right? To ask a human being to sit there, just finger over the button, like, oh, it's getting close, shut it all down. That's not a good use of a human's time, right? It's continuous. We want to be doing it all the time, doing these experiments, perturbing the system so that we see how the boundary is shifting over time, right? That's very important. Is the boundary kind of creeping in on us? What is our operable space? So that's something that's best accomplished through tools. I don't care what the tools are. I don't care if you just have a real bash wizard hanging out with you, or you buy a tool, or you dedicate a whole team to it. I don't care. All that I'm saying is that you need a way to safely perturb the system. You need a way for those experiments to understand when they have reached that safety boundary and shut down, pull back, clean up neatly, right? Because safety is the prerequisite. We are not trying to bring down production. We're just trying to find out where that safety boundary is. I hope that's very clear. I don't want anyone going to work later this week and taking down production and blaming it on me. That would be very sad. So what we're trying to do here is understand in our system, how have we normalized deviance? So if that safety margin is creeping in on us, or we're being pushed into the safety margin, we're trying to come up against that margin and map it, how it's moving over time, so that we can understand. We don't, as humans, we will have the tendency to normalize, right? To acclimate to whatever our new situation is. And that's great, makes us very adaptable. However, we don't want to do that in this situation. So again, that's why we need tools to do this, because the tools won't acclimate to that, right? They'll just perturb the system and tell us where the safety boundary is. So why continuous verification? Why now? I'm sure you're starting to come around to this, but continuous verification is tooling to look at that safety boundary in complex socio-technical systems, complex systems. So those are systems that are made up of the machines and the people, and we're all acting on each other all the time, and everything is kind of in constant flux. And when I talk about complexity, I am talking about these things, right? So our complex systems are acting on themselves. So you will never be able to perfectly, the chat is ridiculous right now, but you'll never be able to perfectly repeat an experiment because the system is acting on itself, right? We are acting on the system and the system is acting on us. It has emergent properties. So the individual properties of each component within the system are not the properties of the system overall, right? Those components come together and exhibit, and they come together with us, and they exhibit emergent properties. So that's kind of what I mean when I talk about complexity, right? So we can never fully predict. We can only recognize what happened in hindsight. Has anyone seen this magical film called The Sixth Sense? I asked this question a few weeks ago, and 2/3 of the people were too young to have ever seen it. And I felt like, yeah, it was really bad. But anyway, The Sixth Sense. So when this movie came out, which I understand some of you will not remember that fine time, but when this movie came out, everyone saw this movie. Everyone saw this movie, right? And what did they say? I knew personally so many people who saw this movie and they're like, I knew it. I knew it. I knew it, right? How many people I know, you all knew someone who said, I knew it. I knew it. Fight Club was the other one. I knew it. I knew when the bus went by, I just knew it. But those people aren't terrible. That is just a human brain thing that happens, right? Once we see something, it's basically impossible for us to unsee it, for us to unknow it, right? So we immediately just build it into our mental model, right? Oh, I get how that all fits together now, so I must have always known that was true, right? So with continuous verification, what we're trying to do, how many times have you been on an incident call and you all hang up, or it's the next day and everyone's talking about how terrible it was? And there's a few people who just, I knew it. I knew exactly. I knew it. If you knew it, could you have told me before it turned into an incident? That would have been cool. I would have liked that, right? The thing is, we usually don't know this, but our brains are just so good at retrospective coherence that we make it all make sense. So what we're looking for with continuous verification is we want to increase our actual ability to predict things within our complex system. So we know that in a complex system, no single person can have an accurate mental model of the system. So we're trying to use tools to increase the accuracy of our mental model and give us the information that we need about how our system is likely to behave. Yes? And if my friend Ansel is in the audience right now, I do hope that you did your homework and watched The Sixth Sense, because I feel like it's an important piece of our culture, global culture. So yes. So that's what we're doing here in continuous verification. We recognize that these systems are in this constant state of flux, and we're trying to build a better mental model of those complex systems. Yes? Yay. Okay. So why is that so dang important right now? Because we had this little thing. Okay, I don't know if you all have heard of it. I like to refer to it as the Dad Pants Manifesto. It was signed in 2001. Some guys got together, they went to a ski lodge, they just got totally wasted and wrote this thing about agile software development. And that kind of became the gold standard for how we're going to develop software. And it was all about this. We want to deliver working software frequently. Go, go, go. Let's deliver tons of working software, right? That's awesome. That's totally cool. I'm down for that, for sure. The thing is, it didn't say in there, deliver frequently and keep it working. It just said, deliver working software, not friends. You got to just keep making it work. And every time you deploy something else, you got to make sure all of it works together again. And every time your customers start using the product in a different way, you got to make sure it works all over again. And we're going to be just deploying constantly. There's going to be a thing called continuous delivery. It's going to rock your world, right? That wasn't really part of the plan at that point. So we got really good at delivering software. Now we need to get really good at making sure it works and just keeps working, and understanding when we are approaching not working instead of just crossing that line. So this is a quote from a great book by my friend Casey Rosenthal and Nor Jones, and you can actually get this book for free right now. You can download it for free if you want it, but it's a terrific book. Yes, so when a gap of expectation exists between two or more engineers separately writing code, then the interaction of that code may produce unexpected and undesirable results. The quicker that can be caught, the more likely it is that the next code written will have fewer gaps. So that's saying that we're all sitting here, we're all writing code separately, right? And we put it together. And even if you're using Ensemble working, you have different ensembles, you're still putting code together ultimately, or you're putting new code together with old code. We're always doing this, and we know we're in a complex system, so none of those people can individually have a complete mental model of the system. So there's always going to be these weird things that come up. I think we need to subtly tweak this now. To point out that, sure, it's between us, the technologists, the makers, right? We have differing mental models that we need to understand how they come together. And our customers and the world is also changing, right? So you can make something that works. And then what happens when COVID hits, right? Your software could still be working, but the way that the world is using it is completely different. So not only do we internally have to come to grips with the fact that our mental models are all incomplete and differently overlapping, but we also don't have the ability to come up with a perfect mental model of how customers are going to use our product or what's going to happen in the world. So we're constantly in this situation where we're integrating our code with itself, and then we're integrating that with the world, right? So that's why these boundaries are always going to be moving in a way that we can't possibly know. So we must create tooling that perturbs the system to the boundary of safety and looks at how that boundary shifts over time. And why is that? Well, my friends, That's because you can go back all the way back to the classics. No woman ever steps in the same river twice, or it's not the same river, and she's not the same woman, right? We are constantly changing, our systems are constantly changing, and the world is constantly changing. And we have to find some safe way to integrate all of that in production. So that's kind of where we end up needing some continuous verification in our lives. This is a real river that I really hike to. But yes, anyway, so that's my whole thing about continuous verification. Here are some books that I highly recommend on the topic or closely adjacent to the topic. And I think that's it. Questions now? Yes, is that accurate? Okay, can I stop sharing my screen?
That is accurate.
Okay. I've been told to leave my screen.
So sorry, everybody's eyes for the big pink fluoro. Thank you.
Not sorry.
So yeah, I mean, I guess my question was the Sixth Sense movie. What is that? And what was that funny round thing you showed on the screen? I must be too young to. Okay, I can't put that off. All right. Thank you, Kat. That was magnificent. And we do have some questions. Everybody bung those questions in the Q&A. I am going to start going through them. I'll start from the top, upvote the ones you like, and they will get answered first. So my first question is from Patrick Chong, and I think he's going back to the graphs. And he says, what about skills boundary? We have economic workload and performance boundary. How do we manage skill set limit?
Yes. So I feel like there could be two questions mixed up in there, maybe, perhaps. So I think one of them is about how we depict the limit of the skills, and the other one is how do we actually manage the limit of the skills. And I think the depiction of the skills kind of, in my opinion, influence multiple boundaries. So I'm not sure that they are a boundary themselves. I think they influence other boundaries. So I'm not sure that it would always make sense to like depict them as a fourth boundary or something on the Rasmussen triangle. However, it's certainly a huge concern, right? So I like to use the idea of skills liquidity, and you can Google that and things come up. But that's basically where we look at what are the skill requirements for a safely functioning system. And then we inventory our current skills to say how near or far we are from that. And then we do that again, of course, over time. And also, if we're looking to create this sort of optionality in our system, if we're looking to manipulate those boundaries in a certain way, what would be the needed skills for that? And then how close are we to that? Can I go turn on a light in here really quick? Because it's gotten dark. The sun has set and I only have one light on. Is that okay?
I don't see why not. We'll just talk amongst
I'll
ourselves. Maybe I'll ask the next question really, really slowly or not. That was so quick. That was it. Okay. Did you want the next question?
Yes, please.
Yes, we're good. Okay. The next question is from David, and he says, how do you know where to tune your tooling to when you first deploy in production? I.e., how do you find that safety margin to begin with?
Dude, that's terrible. It's awful. Thank you for asking that question. There is no good answer, right? Like you can look at the things people have written and said, and you can pick one of those things and try to perturb the system. I guess the one thing that I would say to you is that we're trying to elicit a certain effect from the system, right? We're not necessarily trying to programmatically enact a specific how of getting that effect, right? So if tons of different things could happen, right? Like, oh, what if what if we temporarily lose connection with another data center? Or what if this other service, this database that's total turd just starts to like crap out? Or what if there's some sort of like, hours deep message queue building up or something like that? But then you can say, well, realistically, for this area of the system that's highly critical, all of those things are really just introducing latency. And so then you can just say, what I'm going to do is introduce latency and see how that latency curve, or like round trip latency or something like that, starts to shake out. And if it starts to get like a weird shape or anything like that. But yeah, some people in the chat are saying like, well, go in and like really shake things up in the test environment, and that might give you ideas of where to poke. Totally agree with that.
Could you do some sort of chaos engineering-y stuff to unleash the chaos monkey?
Right, but you have to know what to chaos, right? Like there's like an infinite number of things that you could chaos. Again, that's another reason why I like to keep the near miss log, right? Because if you have a bunch of people who are in there every single day, the things that they're writing down for their near misses are probably a really good place to look for which aspects of the system to perturb to get an idea of the safety boundary.
Cool. Our next question is from an anonymous source who says, how do you manage your boundaries when constrained by a third-party exclusive resource, e.g. API or service only offered by one party? Do you build that service yourself?
Okay, so I think what you're saying is there's a critical component within your technical landscape that you don't own, and that that's where you need to do some sort of experimentation, or that component has a direct impact on the safety boundary. Is that right? I know there's a lag, but maybe this person can, not trying to take away your anonymity, but I hope that's it. We can only do what we can do, right? But you can ask which in the interactions with that, whatever third-party component or proprietary component, can we introduce any sort of perturbations? And then can we introduce safety measures, right? And isolate as much as you can. But I don't know. I have such mixed feelings about this, right? Because sometimes it's like, oh my gosh, why are we letting a third party operate something that's mission critical for us? But also you want to be able to enable higher order innovation within your business, right? And that means you have to be able to treat some of the underlying components as like off-the-shelf products or utilities, and that kind of is what it is. So I probably could like do a whole talk on just that, looking through different, I don't know. You can always just start by saying, is there any way we can do a game day with some of these chaos engineering scenarios around this component, where we can get representatives from that vendor or some sort of specialist or whatever in the room with us and just run a game day? So do something during normal business hours to see how the components interact.
And if you'd like to hear that talk from Kat, please put your vote in the chat. Okay, next question is from Lee Campbell, and he says, is there some sort of continuum here? Step 1, come up with your safety boundaries. Step 2, learn to experiment safely. Step 3, automate.
Yeah, yes, of course. Yeah, totally. There is a spectrum here, and I would never say, like, I think one of the number one mistakes that I see people doing is that they want to create like a full chaos engineering or continuous verification suite in a non-production environment. And the very first time they actually do any of those verifications or run those experiments in production is like when they deploy the whole thing, right? That is, I cannot tell you, like going to be so extremely painful for you. Certainly you should get an idea of like what defines safety for us. And that might not be anything that is directly tied to revenue, but what is a measure of safety for us? Then in production, we're going to manually perturb these other factors that we believe will have some sort of impact on safety. And we're going to see, do we actually have an impact? Are these the right things? And then we can try to come up with experiments, but you have to test the waters in production, right? And so that will look like something like a game day, or that will look like whatever. You can't just build this big old continuous verification doodad and like nicely promote it through environments. Does that answer the question, Lee?
There's quite a few questions I'm kind of going to roll in together where people have asked, which tools? Are there any recommendations of tooling to achieve continuous verification? Is there a framework for continuous verification?
There's no framework, I would say, right? Like the space is really emerging, and the very few vendors who are in the space, I think even they would agree that they are not as much competing with each other as they are competing with homegrown tooling, right? Because it is just emerging, and then different tech stacks and all of these things, wildly different architectures. And especially when you get into continuous verification, it's not as simple as, we're not asking, is this safe, right? Kill this pod, kill this instance, can the service recover? In continuous verification, we're saying, okay, what is the boundary of safety? We're going to get up really close to that. We're going to pull back off of that. So that is really, in a lot of ways, context specific. Of course, Dave mentioned earlier, Verica is doing great work in this space, but it's all emerging right now, right? Like if you want to do this at home for yourself, that's totally fine. You're not going to get yelled at for not going out and buying the right tool. Sometimes your context is just specific and you need to do what you need to do.
Okay, one last question. So talking about safe systems, how have you applied this, or I guess would you apply this in safety critical systems like medical, defense, etc.?
Yes. So I have done that, right? But that was done with great care, right? And so you just have to make sure that safety is a prerequisite. So if there's any doubt as to whether this experiment or this verification will have a safe outcome, it all just needs to shut down, right? Because we're not trying to cause chaos in the system. We're trying to find the safety boundaries. So we always have to err on the side of safety. However, once we have that information and can see the boundaries shifting over time, it is terrific for our systems, right? And if you do have something that's truly mission critical, and you can see how the safety boundary is changing over time, like that is an incredible, incredible feeling, right? And yes, someone just said, this is always the thing that people bring up, right? Cyber physical systems. So your pacemaker or autonomous vehicles or whatever the case may be. And if you're really interested in that, I would highly recommend looking up Tiani Jones. She's someone who's doing a lot of work with how we can experiment in cyber physical systems that are mission critical. So she would definitely be the person I would go to on that.
Fantastic. Thank you so much for your talk and for your time this evening for you, Kat. And it's been wonderful to have you. And yes, everybody show your love and your virtual applause in the chat.